Good morning, everybody. Let me know if you can hear me okay. Okay, good. We'll get started with going over the do now, just to shake the cobwebs off. So we have a decomposition reaction here, and we have to calculate the moles of oxygen gas produced from 5 moles of hydrogen peroxide. To do that, we have to write a mole ratio. We're interested in the hydrogen peroxide and the oxygen gas. So we can write 2 mole ratios for that. We just take the coefficients that are in front of each compound that we're interested in the chemical equation and write it as a fraction. Then you write the reciprocal. We're trying to figure out how many moles of oxygen gas we'll make, which means we need to cancel out the moles of hydrogen peroxide. So we're going to use this one. When you do the math, you're just dividing 5 by 2. And that's what you should get. Do we have questions on this? Because this is kind of taking it a few steps back from what we were doing last week, and I'm going to try to ease us back into it. I know there aren't that many of us, but I need some participation. Let me know how we're doing with this one. Does this at least ring a bell if you couldn't get it done? Does it look a little familiar? Okay, thank you. So, we're going to finish up this chapter this week. And before we get into the new stuff, I'm going to do a couple of practice problems with you all to remind you of what we did, because I know we just had an exam, and Chapter 9 was not on that exam. So Chapter 9 is probably gone from your brain. So let's try to bring it back. We introduced interpreting chemical equations, the mole ratios, and then we did some stoichiometry problems. The first type of problem that we did was a mass-to-mass problem. This is where you're taking the grams of one substance in a chemical equation, and you're trying to convert that to grams of another substance in a chemical equation. So we'll walk through this. I'll ask you some questions as I solve through this problem, and hopefully that'll help you to refresh again. What is the mass of zinc oxide that can be prepared from 1 gram of zinc metal? Remember, you're not always going to have this handy little title that tells you what type of problem you have. So you need to classify the problem. We're starting with 1 gram of zinc, and the question is asking about the mass of zinc oxide. So that shows us it's a mass-to-mass problem. In general, the way that we solve a mass-to-mass problem and I'm going to write this in generic terms of A and B, and then fill it in with the terms that we're going to be using. So this generic one you're going to want to have in your notebook. So let's say that we're starting out with grams of A. The first thing you need to do is convert those grams to moles. And that's using the molar mass of A. To convert that to moles of B, which is your other substance in the chemical equation, you need a mole ratio. And it's going to have the form factor of B over A. And I'll show you what that means in a second. The final step is to take the moles of B and convert to grams. That's again using a molar mass, but this time the molar mass of B. For what we're doing, we're going to call the zinc the A, and zinc oxide is B. So we're taking the grams of zinc from the problem and converting it to moles of zinc using the molar mass. Then we go from moles of zinc to moles of zinc oxide. And we need a ratio for that. So that B over A is zinc oxide over zinc. Then we take those moles of zinc oxide and using the molar mass, convert to grams. So I want you to take a minute and using your periodic table, find the molar mass of zinc and the molar mass of zinc oxide and put it in the chat. We've got the zinc. Still waiting on the zinc oxide. You're just taking what you see on the periodic table for zinc, what you see for oxygen, and adding them together. Thank you. Now let's start filling in some numbers. We're starting with 1 gram of zinc. And now I need to put a unit factor for converting those grams to moles. So where am I putting grams? In the top or in the bottom? Yep, I'm putting them in the bottom. Now I need a mole-mole ratio that relates the amount of zinc oxide to zinc. So we're looking at these two things in the chemical equation. What's my mole ratio going to be? Yeah, it's going to be 2 moles over 2 moles. Just make sure that it's 2 moles of zinc oxide over 2 moles of zinc. So that B over A in the generic formula, our B is zinc oxide. So you write the number of moles from the chemical equation for zinc oxide on top and zinc on the bottom. Not a trick question. The final step, we have to convert the moles to grams for zinc oxide. So where am I putting my grams this time? Top or bottom? Right, I'm putting them on the top. When we make sure that our units cancel, the first thing we did was figure out the moles of zinc. Then we figured out the moles of zinc oxide. Then we got all the way to grams. So each time you cancel each step, you can see that it matches up with your plan. When you put that into your calculator, you should get 1.24 grams of zinc oxide. So that's the recap for mass to mass. We did those last week. We're not going to do them again this week. I just wanted to give you the recap. Are there any questions? If not, you can say you're ready to move on. All right. Now we'll review mass to volume, which was the other problem type that we did. So, what is the volume of oxygen gas needed to fully react with 1 gram of zinc metal? And this is at STP, okay? We still have the 1 gram of zinc, but this time we're going for a volume of oxygen gas. I'll give you the generic, how you solve it, and then I'll put up our plan and we'll fill in some numbers just like before. The first step is always getting to moles. The second step is always getting to moles of B using that ratio. The third step is what's different. We're trying to get to a volume we have to use molar volume here, which is something we talked about in chapter 8. Remember, with molar volume, we're saying 1 mole of gas has a volume of 22.4 liters at STP. And that's how we can convert moles of our gas to liters of our gas. The A in the generic form is always going to be the given information. We were given the mass of zinc, so that's our A. We need to find the volume of oxygen gas, and that is our B. So let's fill this in more specifically for what we're doing. So the first step is identical to the problem that we just did. The second step is similar, but instead of zinc oxide, we're looking at oxygen gas. And the third step is molar volume, which we will address when we put together our equation. So is everybody with me so far with this plan of how we're going to solve the problem? All right. So let's start filling in the numbers. Like I said, the first step is exactly the same. Now we need a mole ratio. What is our mole ratio going to be? This is your hint right here. Is the mole ratio hard for you guys? Okay. So with the mole-to-mole ratio, in the generic form, we've got B over A, right? So that's what we're trying to find over what we know. Our B in this case is oxygen gas. The A is the zinc. So since you know that, you can go to the chemical equation and say how many moles of oxygen gas are there. So tell me, how many moles of oxygen gas are in the chemical equation? There's 1 mole. So you write that one on top. How many moles of zinc are in the chemical equation? You write that on the bottom. So if you fill in this plan and you label your A and your B, then you'll always know what to put on the top and what to put on the bottom. So I will post some practice for Chapter 9 and make sure to include some mole ratio stuff. Okay. The final step with this is using molar volume. We have a unit equation here. 1 mole of gas is equal to 22.4 liters, and this is at STP. We can write 2 unit factors. If we need to go from moles to liters, which one am I going to use? The first one or the second one? I'm going to go with the second one. Try putting this into your calculator and let me know what you get. So we only need 3 sig figs here. So it should be 0.171 liters of oxygen gas. Do we feel a little bit better about the mole-to-mole ratio? We're going to keep on doing these. Every one of these problems is going to need a ratio. So we'll keep practicing. Okay. Now we're going to do volume to mass. And this is kind of where we left off last week. So we did mass to volume, where we took some number of grams and converted that to some number of liters of a gas. Now we're going to start with some number of liters of gas and convert that to a mass. How many grams of sodium chlorate are needed to produce 9.21 liters of oxygen gas at STP? We always want to identify the problem. We're starting with the volume, and we're trying to get to a mass. So how many grams? That means a mass. So that tells you it's a volume to mass problem. So we're going to kind of flip what we were doing in the last problem with mass to volume. Instead of starting with grams, we're starting with liters. So I'll write out the generic how to solve it and then fill in the plan just like I've been doing. You're starting out with liters of A, and I'll keep the same color coding. We need to get to moles of A. How did we get from liters to moles last time? Or we went from moles to liters. How did we do that last time? If we're going back and forth between liters and moles and liters, we have to use molar volume. That's what we did before. Then we use a mole-mole ratio to figure out the moles of B. Finally, you use the molar mass of B to get to grams. In this problem, the A, our given, is oxygen gas. And what we're trying to figure out, the B, is sodium chlorate. So let's fill in the plan with our specific variables. We're starting with liters of oxygen gas. And we're going to get some moles. Then we're going to get to moles of sodium chlorate using that ratio. And for our ratio, it's going to be the sodium chlorate over the oxygen gas. Then we convert to grams using the molar mass. Take a second and figure out what the molar mass of sodium chlorate is and put it in the chat. While you do that, I'm going to start setting up the equation here. Yep, that looks about right. I think I had 3 decimal places, but not a big deal. You'll get the same answer. So we've got our molar mass. We can start setting up the equation. For molar volume, we said 1 mole of gas is equal to 22.4 liters. We're trying to go from liters to moles. So where am I going to put that 22.4 liters? The top or the bottom? We're going to put them in the bottom. That means 1 mole goes in the top. Now we need to figure out that mole-mole ratio. This is your clue to tell you what goes on top and what goes on the bottom. So what's my mole ratio? Remember, you have to look at the coefficients that are in front. There we go. The other way that you can think about this is you need to cancel out the moles of oxygen gas, right? So the oxygen gas has to go on the bottom. And for the mole-to-mole ratio, you're not creating anything new. You're just taking the numbers from the chemical equation. The final step is using the molar mass. We make sure that everything cancels. So we got our moles of oxygen, then the moles of sodium chlorate, then the grams, which is what we were after. And when you put all of that into your calculator, you should get 29.2 grams of sodium chlorate. Questions on this? Because I'm going to have you try a problem next. If you're ready to try a problem, let me know that too in the chat. We just not ready for anything. Okay. I know it's early, y'all. And I know this ain't the easiest concept. But it makes it go faster when we participate. Okay. So how many grams of sodium chloride are produced when 9.21 liters of oxygen gas is produced at STP? So I'll help you set up the problem and then I want you to try it. We're still starting with the same volume of oxygen gas, but we're trying to figure out how many grams of sodium chloride we make in addition to that gas. So the oxygen gas is the A, and sodium chloride is the B. Use that generic formula, fill in your plan, then write out your equation and give it a shot. I'll give you 5 minutes to get a head start. Alright, it's been almost 5 minutes. How are we doing? Are we stuck? Did we get somewhere? Did we get to write a plan? Talk to me about how this problem is going. Let me know if you even started it. Let's just be real with each other. Do you feel like you could start this problem? Okay, you can share your answer if you got an answer. If you didn't get an answer, let me know what's going on. Okay. For those of you who did not get an answer, did we try the problem? You're not going to lose points if you're like, man, I ain't try it because I feel like I can't. If you tell me that, then we can fix it. Okay. So if you tried it, how far did you get? Because the key part is writing that plan and filling in the numbers. So as I go through, let me know where you got stuck. And if you felt like you just weren't prepared, okay, we can fix the mole ratio part. But if you feel like, man, I feel like I can't try this, let me know. Because we can do something to try to help you feel more confident about it. Oops. Starting off wrong. So we're starting with the same 9.21 liters of oxygen gas. And this is just writing out the plan. We're going to get that to moles using molar volume. Then we need a mole-mole ratio. And that's going to be B over A. Our B is what we're trying to find. That's sodium chloride. The A is oxygen gas. Then we have to go from moles to grams. And that will require a molar mass. When we fill everything in, that's our given information, 9.21 liters. We're trying to go from liters to moles, so the orientation of this unit factor will be the same as last time. I'm going to have liters in the bottom. For the mole ratio, it's always what we're trying to find over what we already know about. We're trying to figure out how much sodium chloride we make. So that means the moles of sodium chloride from the chemical equation go on top. We're given information about the oxygen gas. So the moles of oxygen gas that are produced in the chemical equation go on the bottom. Does that help some, Cameron? Good. No problem. See, when you tell me, I will help you out. You know that. Now we need to go from moles to grams. And this is what I got for the molar mass of sodium chloride. So when you do all that, and you take into account sig figs, you should get 16 grams. So how do we feel about that now? And if you just need time for it to sink in, that's cool too. You can let me know that too. Just let me know that you're with me. All right. So we've got one more problem type to do. We did mass to mass and mass to volume last time, and we did a recap. We also kind of did the bonus of volume to mass, which isn't really a different problem type. It's just kind of flip-flopping. The third type is volume to volume, and these are the easiest. So I'll do an example for you, and then we'll work through some problems. Volume to volume problems, you're always looking at gases. And it doesn't have to be at STP. They just have to be at the same temperature and pressure. How many liters of oxygen react with 37.5 liters of sulfur dioxide in the production of sulfur trioxide gas? So here we're assuming everything's at the same temperature, same pressure. And instead of saying moles of things, we can say liters. So the generic one for this, we're starting with liters of A. We can get to liters of B directly by using a mole-mole ratio of B over A. And that's literally it. So instead of writing moles, you can write liters. We're starting with 37.5 liters of sulfur dioxide gas. And we're trying to get to how many liters of oxygen gas we need to react with it. There's the sulfur dioxide. There's the oxygen gas. what's our mole ratio going to be? If the sulfur dioxide gas is A and the oxygen gas is B, using the chemical equation, what's my ratio going to be? So I wrote moles. We don't have to write moles. We can write liters, because we're dealing with all gases and we're assuming that they are at the same temperature and pressure. So instead of writing moles, you can write liters. Put that in your calculator. Let me know what you get. Yeah, your calculator is going to tell you 18.75. We want 3 sig figs here because we've got 3 with our given information. So we're going to call it 18.8 liters of oxygen gas. That's volume to volume. You start with the volume, you write a mole-mole ratio, but instead of writing moles, you can write liters because you've got all gas and it's all the same conditions. Questions on this? Because I have an example for you to try. So let me know if you're ready to try it or if you need me to go through this again. Then let's try it. How many liters of sulfur trioxide gas are produced from 37.5 liters of sulfur dioxide gas? I'll help you get set up. I'll give you 3 minutes to give it a shot, and then I'll start working on it. Alright, let's give it a shot. If you got an answer, you can put it in the chat. But I'll start setting up the problem. And if you got stuck, you can let me know that too. So we literally have one step. What's our mole ratio going to be? Good job. It's going to be 2 to 2. I'm so used to writing moles that when I get to volume, my hand already starts making the M before I even realize it. You shouldn't need to pull a calculator out for that. Questions on that? Okay. Here's one more problem I want you to try. I'll help you get it set up, and then I want you to give it a shot. How many liters of oxygen gas are required to make 15 liters of sulfur trioxide gas? So we're starting there. We're trying to figure out how much oxygen we need. I'll give you another 3 minutes, and then I'll check back in. Let's get started. We have 15 liters of sulfur trioxide gas. We're trying to figure out how many liters of oxygen gas. What is our ratio? Yes, 1 to 2. And that's exactly what you should get. So with sig figs, it should be 7.50, but I ain't gonna hold you. Oh, that is totally the wrong unit. So how do we feel about these volume to volume problems? Are we good on these? It seems like y'all are getting the mole ratio a little bit better. That makes me happy. So I think this is a good time for a break because we're going to move from here to limiting reactants. So it's a little bit of a jump. So it is about to be 9:15. Let's break till 9:25. Good 10-minute break. And take 10 minutes, shake your brain out, and come on back. Alrighty, everybody. Break time is over. We're going to get back to it. So we have a couple more concepts to go before this chapter is done. The first one is the limiting reactant concept. Before we start talking about the chemistry, let's just bring it to something that we all can relate to. Let's say you're making grilled cheese sandwiches, okay? Real basic. At the very minimum, you're going to need some bread and some cheese. 2 slices of bread, couple slices of cheese. This ain't gourmet, just straight up, gotta make something quick. If we wrote that as an equation, it would be 2 slices of cheese plus 2 slices of bread gives you 1 sandwich, okay? And we're not going to talk about putting butter on the outside or anything like that. We ain't talking about that. That's too complicated. If I had 10 slices of bread and 2 slices of cheese, how many sandwiches could I make? Let's see how many people are back from break. You can only make 1. Yeah, you've only got enough cheese for 1 sandwich. If you're going to make a grilled cheese, you got to have some cheese. So in this case, the cheese is limiting. You can only make 1 sandwich. And you've got excess bread. You have enough bread to make 5 sandwiches, but you've only got enough cheese for 1. It's the same concept with chemicals. Sometimes a chemical might be expensive or hard to make, and you've only got a little bit of it. And you mix it with something else, and you only make a small amount. So the limiting reactant is the one that's used up before everything else. In our example, that was the cheese. We only had 2 slices, and then that was it. The bread, we had plenty of bread left over, but we can't do anything with it. Does that concept make sense of a limiting reactant? Okay, good. So let's show what that means with chemistry. Not as interesting as grilled cheese sandwiches, but we'll get through it. Let's say that we've got 5 moles of iron and 3 moles of sulfur and we heat it. How many moles of iron 2 sulfide are formed? We're told about 2 different reactants, and we have to figure out how much product we make. That's going to be the form factor for a limiting reactant question. You have information on 2 reactants, and you have to figure something out about the product. What we're doing here is really 2 small problems. The first problem is if we have 5 moles of iron, how many moles of iron 2 sulfide can we make, assuming that we have all the sulfur in the world? The second question is if I have 3 moles of sulfur and all the iron in the world, how many moles of iron 2 sulfide will I make? So let's answer these 2 questions first. we need a mole ratio. And the mole ratio is still going to be B over A. So what is our mole ratio going to be if we're trying to figure out how many moles of iron 2 sulfide we'll make from all of this iron? Not 5 to 1. So remember, you're going to the chemical equation. So next time I'll write the A and B over the chemical equation. I think that might make it a little bit clearer for you. So let's just do that now. It's 1 to 1. So we're going to make 5 moles of iron 2 sulfide. I'll do the next problem in blue so that we can kind of see the difference. Now we're doing the same thing with the sulfur. What's my mole ratio? It's still 1 to 1. So that's the first part. We figured out how much we would make if we only had the iron, how much we'd make if we only had the sulfur. Now we have to figure out which one makes the least amount of product. So you figure out which one is the smaller number. 5 moles or 3 moles? Which one's smaller? That's an actual question, not a trick one. All right. So with our question, which one makes the least amount of product? We've got 3 moles of iron 2 sulfide. That means the sulfur is limiting. With these limiting reactant questions, you have to choose which one makes the least amount of product, because that's the amount of product that you're going to report. We could only make 3 moles of iron 2 sulfide from 3 moles of sulfur. So we could mix it with 5 moles of iron, 10 moles of iron, 100 moles of iron. We can only make 3 moles of iron 2 sulfide. Does that make sense? Okay. So now I'll give you a little bit more of a complicated example. We're going to combine the problem types that we've been doing, the mass to mass, mass to volume, and volume to volume, with the limiting reactant problems. So here we go. How much molten iron is formed from the reaction of 25 grams of iron 2 oxide and 25 grams of aluminum? Again, we see two given amounts for two different reactants, and we're asked about one of the products. So that clues you in that you have to do a limiting reactant type deal. How much molten iron? Since we're given grams, that means we need to figure it out in grams too. So this is combining mass to mass and limiting reagents, which I abbreviate LR. And reagent and reactant are the same thing. You can use them interchangeably. So we're setting up two mass to mass problems, which I know, great joy, right? The first one, we're taking the 25 grams of iron 2 oxide and figuring out how many grams of iron we can make. For the second one, we're taking 25 grams of aluminum and figuring out how many grams of molten iron we can make from that. So it's very similar to what we just did, where we solved two problems and then we choose the one that makes the least amount of product. So I'll walk you through it. I'm going to ask you some questions along the way. So this is mass to mass. We're starting with the iron 2 oxide. How do I convert grams to moles? Molar mass, right. So I calculated that molar mass. You can check me on it if you want to. Now we need a mole-mole ratio. What is our mole-mole ratio if we're trying to figure out how much iron we make from iron 2 oxide? It's 3 to 3. Make sure that iron is on top and the iron oxide is on the bottom. Then we use the molar mass of iron, which you just look at the periodic table. And when you do all of that, you should get 19.4 grams of iron. But we're not done yet. That was only part one, figuring out how much molten iron we'd make if we just had 25 grams of iron 2 oxide and all the aluminum in the world. Now we have to do the reverse, where we have aluminum, 25 grams, and we've got all the iron 2 oxide in the world. So that's the molar mass of aluminum straight from the periodic table. And you know what I'm about to ask you. What's our mole ratio? If now we're dealing with aluminum and iron. It's 3-2. 3 moles of iron goes on top. 2 moles of aluminum at the bottom. This last part is going to look the same because we're taking moles of iron and converting to grams. So how much molten iron will we make if we mix 25 grams of iron 2 oxide and 25 grams of aluminum? Which one is it? We're going to make the 19.4 grams because that one's the least amount of product. Which reactant is the limiting reactant? The iron 2 oxide. So the general process, you figure out how much you'll make from each reactant. Then, whichever one makes the least amount, that's how much product you'll make. And the limiting reactant is the one. It's the reactant that you use to figure out that amount. So does that concept make sense? We're kind of putting it all together here. All right. So let's try another one more together. Same equation, same amounts. Now we're looking at aluminum oxide. So if we have 25 grams of iron 2 oxide, how many grams of aluminum oxide will we make? That's the question for number 1. The second question, if we take the aluminum, how much aluminum oxide will we make? And then the third one is, what's the limiting reactant? How much are we actually going to make? So let's start with the iron 2 oxide again. It's going to be the same as last time. What's my mole ratio this time? We have iron 2 oxide. We're trying to figure out how much aluminum oxide we make. So when you're doing these at home, with your homework, make sure that you label the A and B so that you get that mole ratio right. When you put all that into your calculator, you should get 11.8 grams. Now we get to do the same thing with 25 grams of aluminum. Do the colors help with trying to keep things consistent so you can recognize it? I try to keep it consistent if it's helpful. So let me know if doing the colors are good. Okay. Then I will continue. So that's the first part. We're converting the moles. We're converting to moles of aluminum. And you know what I'm about to ask you. What's my mole ratio? Y'all are getting it. Good, good. So now we've got 1 to 2 for our mole ratio. And this last step, again, is going to look exactly like the top because we're converting moles of aluminum oxide to grams. So we've got our two answers to choose from. We're either going to make 11.8 grams or 47.2 grams. So which one is it for this limiting reactant problem? We're going to make 11.8 grams. And again, the iron 2 oxide is the limiting reactant. Questions? If not, let me know you're ready to move on. All right. So I have one for you to try. How many liters of sulfur trioxide gas are produced from 18 liters of sulfur dioxide gas and 18 liters of oxygen gas? So this one is volume to volume and limiting reactant. I'll give you about 5 minutes to try to set it up on your own, and then I'll start working through it. I'm going to go ahead and get started with setting up the problem. We said it's volume to volume and limiting reactant. That means we've got two problems to solve. The first one is if we have 18 liters of sulfur dioxide gas, how much sulfur trioxide gas will we make? The second question is if we have 18 liters of oxygen gas, how much product will we make? Thankfully with these, it's one step. All we have to do here is figure out the mole-mole ratio. So that's the first part. 18 liters of sulfur trioxide gas is what we can make from 18 liters of sulfur dioxide gas. We do the same thing for the oxygen. Once we get here, we have to figure out which one makes the least amount of product. That's going to be the 18 liters. So how do we feel about that one? Did anybody have questions? Anybody get stuck? Or are we ready to move on? The final concept for this chapter is percent yield. When you're doing chemistry in the real world, things don't always work out perfectly. In fact, they never do. So when you're doing a reaction, the amount of product that you make is actually called the actual yield. What we've been calculating with these different stoichiometry problems is the theoretical yield. That's the maximum amount of product that you would make if everything aligned properly in a perfect world. The actual yield is what you make in the lab. So maybe you didn't scrape out all of your reactant from the weigh boat. Something didn't go right. You dropped some product. Things happen, okay? The way that you calculate the percent yield is by taking the actual yield and you compare it to the theoretical yield. You put the actual on top, theoretical on the bottom, and multiply by 100%. So this is what you'll need to know for calculating the percent yield. Again, the actual yield is what you make in the lab. You'll always be told what your actual yield is with problems from me, because you can't really figure that out. So I will tell you how bad of a scientist someone is, and then you can calculate the theoretical yield, or I can be nice and give it to you. But again, the theoretical yield would be like a mass to mass problem, or a volume to volume problem, or something like that, to figure out the theoretical yield. And then I could tell you the actual yield, and you could calculate the percent yield. But before we get there, let's just keep it simple and straight up calculate the percent yield. So let's say a student performs a reaction and they obtain 0.875 grams of copper to carbonate. The theoretical yield is 0.988 grams. What is the percent yield? We said that our equation is actual over theoretical times 100%. What's my actual yield from this problem? We've got two numbers, 0.875 grams and 0.988 grams. Which one of them represents the actual yield, what the student got in the lab? If you need me to rephrase or re-ask a question, don't be afraid to say that. That's totally fine. Yep, that's exactly what we're going to do for the actual and theoretical. then you have to take that ratio and multiply it by 100%. Put that in your calculator and see what you get. Exactly. So you should get 88.6%. I want you to try a problem on your own. Same exact problem, slightly different numbers. And you can put your answer in the chat. I'll write it out, but that is the right answer. So we need 3 sig figs there, but I ain't gonna hold you for right now. Your percent yield should be 75%. So that's the simple version. We gotta ramp it up a little bit. After combining 10.5 grams of iron 2 oxide with excess aluminum, 6.25 grams of iron were produced. What is the percent yield of the reaction? So here we're combining a stoichiometry problem type with percent yield. Let's identify the numbers that we have in the problem first. The first part of this sentence, 10.5 grams of iron 2 oxide with excess aluminum, that's telling us about the amounts of the reagents that we have. The second part tells us how much iron we made. That's the actual yield. So we know about one reactant, how much we started with. We know how much we actually yielded from the reaction, but we don't know the theoretical yield. For that, we have to do a calculation. We have to figure out how much iron we would make in a perfect world. And that's a mass-to-mass problem. Does everybody understand how I pulled out the numbers and assigned them to what they are? Because you will need to do this. One mistake that I've seen over and over with this type of problem is you see these two numbers and you assume you divide one by the other. Don't make that assumption. Just because you see two numbers and percent yield, you have to figure out what those numbers mean. Don't jump to conclusions. So let's do the theoretical yield calculation first, which is a mass-to-mass problem. Starting with 10.5 grams of iron 2 oxide, we have to get to moles. Then we have to go from moles of iron 2 oxide to moles of that molten iron. The last step, use the molar mass of iron to figure out how many grams of iron you would make in a perfect world. That's our theoretical yield, 8.16 grams of iron. Now we're ready to calculate the percent yield. The actual yield was given in the problem, 6.25 grams. The theoretical yield we just calculated, 8.16 grams. Multiply by 100%, and you should get 76.6% as your percent yield. So we just combine the stoichiometry problems with percent yield. Does everyone see how that worked out? So I don't have an example for you to try. I figured by this point y'all might be a little bit tuckered out. But you will have something like this on the exam. So there's no exam 5. There's no exam for chapters 9 and 10. It's just going to be on the final. And that brings us to the reminders. There's no office hours this week. Dr. Hefner is going to be Mama Hefner once I'm finished teaching on Tuesday. So no office hours. You don't have any assignments due this weekend, though I do recommend starting your chapter 9 for mastering chemistry. Those assignments are due Sunday, November 15th by 11:59 p.m. It might take you a little bit longer because these problems are more involved. So make sure that you get started early and you can bring your questions with you next week, either to class or to office hours next week. We have a final exam, and there's a final exam schedule. We were doing the, take the exam over this course of 3 days, but we've got some time between now and the final exam. There's a scheduled time for us to take it. That time is Monday, December 7th from 8 to 10 a.m. So as usual, your exam will be online. You'll take it during that 2-hour window, and then you'll be done with the class. We'll figure out if you guys want some kind of a review session or just office hours or something like that in between Thanksgiving and the final. So we'll figure that out probably next week. If you don't have any questions, that's all I have for you. If you do have questions, you can stick around and ask.